Okay, so this is a video series. Basically, we're going to do a few videos for exercise 4 of the Advanced GIS book, where we will basically do topographic differencing using LiDAR and other digital elevation models. And so this will be a several-part video. The first video, this one, will look at where we can download data sets such as LiDAR and how we need to compare and find information on the metadata for LiDAR and other digital elevation models. So we know whether or not they're digital terrain models, surface models, what their resolution is, coordinate systems, etc. So that'll be part one. Part two will be discussing registering the data sets so that they're in similar coordinate systems or the same coordinate system and datums, and the pixels are aligned so they can be differenced. And then part three, we will part three will probably be combined with part two, and that'll be differencing the digital elevation models in raster calculator. And then after that, we'll have two different videos looking at comparing the different difference maps that we make between different age data sets, how we can compare them visually with histograms, using profiles, and then how we could think about quantifying change potentially using something like zonal statistics, which may or may not be as interesting as we want it to be for this particular example. But the example we're going to look at is, I'll show you here in the GIS project, is basically along the Diamond Fork River and Spanish Fork River intersection up US Highway 6, just outside of Utah Valley. So this is a popular field site for geomorphology, maybe geospatial field methods, and other courses at UVU. It's a nice site because there's rivers, river terraces, and landslides such as the Schertz Lake landslide and the Thistle landslide. So we're going to look at LiDAR in this area. Okay, so where to get LiDAR data? A great resource is Open Topography. And in this case, the reason I chose this site is one, because it's local, two, because there's two different high resolution topography data sets available for the site. So the first one we're going to download or have downloaded is the 2017 Mapping of Diamond Fork River data set, which is the red outline here. That was flown for something called National Center for Airborne Laser Swath Mapping, probably for a graduate student, I believe, at Utah State University as part of their master's or PhD work. So they got a grant for that. It is now available on Open Topography for anybody to use. But then also for this area and much of the rest of the US, you can download these high resolution 1 meter data sets called the 3DEP data set. And so there's one from 2018. 3DEP data was produced for this area, and that's shown in green for this larger area. So we can download the 2017 data by just saying get raster data, and then you have to select the area you want, and you tell it what you want, digital terrain, and fill out your email address, and submit or sign in. If you sign in, you can download more total area at a time. You will need to sign in if you want to use 3DEP data, because it says data sets are available for those with academic access, and that's with .edu addresses such as yourself. So you'll need to create an account with Open Topography using your .edu address to get access to this data. You can also get access to this data through the Utah's UGRC raster data discovery app, but that you have to download in tiles, whereas this you can download as one block. And so then you'd get point cloud data and follow a similar procedure. I've already done this, so I'm not going to take too much time to show you that on this video. You'll also want, we're going to, for this video, we also getting some data from the Utah Geographic Referencing Center, in this case, autocorrelated DEMs. And I originally selected this red polygon here, but I ended up just using this tile right here. So you just click on the tile, right click, save as. This will come downloaded as what's called an, well, it'll come as a zip file. As you extract the zip file, it'll have something called an ASCII grid. And so you have to extract all of these data sets from zip files after you download them. The zip files are usually used for downloading GIS data sets because normally there's multiple files that are a part of the GIS data set, as you're probably remembering from feature classes in Introduction to GIS. But even for rasters, there's usually more than one. As you're downloading these files, you'll want to always get your metadata and reports for the files to learn about what's going on, how accurate are these data sets, what coordinate systems are they in, what vertical datums, etc. So for instance, and you really need to hunt around in some cases. So like if we go back up, if we go to Open Topography Mapping of Diamond Fork, we can see some nice, clearly it says metadata to download. You click on those. Those are actually all basically telling you the same thing in different formats. But there's another thing that's survey report, which is also actually quite critical. And that's what I've opened here. The survey report tells us the coordinates and the geoid model, or the vertical datum. If we go back out here, it says, oh, coordinate system. Oh yeah, NAV, North American Vertical Datum 1988. That's the coordinate system, but that's not the geoid model. And so I had to hunt around and find that report to see that. It didn't say so on the metadata. And so, you know, even though Open Topography is obviously really good about preserving metadata and all these resources here, is not standard where all these things are going to show up. The company that produced the metadata is not the one that's delivering the data to you. And so that's why it's in multiple places here. And so we need to be really careful about that. The other data set that I'm going to show in this video is a global DEM called ALOS World 3D 30-meter data. And so I downloaded that from here as well. So we are going to look in this video example at this 30-meter ALOS data set, a 5-meter digital elevation model. So these are both kind of what I might call regional to local digital elevation models. And then as we get to LiDAR, we're definitely thinking about local digital elevation model. So we'll have 4 data sets overall. The LiDAR is actually only separated by about a year. So it was flown in 2018 and 2017 for two different projects. Actually, I just downloaded the 3DEP one as a 1-meter data set. If you go to the UGRC, you can get it as a 0.5 meter as well, but I didn't do that. So I downloaded as a 1-meter data for 2018, a 0.5 meter from Open Topography for 2017, 5 meter for UGRC. The ALOS 30-meter data set, it says 30 meter, but it's a world geographic data set. It's really quoted in arc seconds of about 30 meters equivalent. But for Utah's latitude, that translates into about 27.4 meters per pixel. So it's not 30 meters. So keep that in mind. The coordinate systems, some of them are different. So the two LiDAR data sets are both in NAD83 UTM Zone 12 North, as is the UGRC 5-meter data set, although they may be referenced to different CORS station surveys. So like the one from 2006, the 5-meter is referenced to 1996. And I think obviously this one is to 2011. So different stations relative to tectonic plate motions and things like that. So there will be difference in their horizontal positions, potentially on the order of millimeters of change or centimeters in Utah over that time, just because of plate tectonics. So it's important to keep those things in mind. We're probably not going to transform that horizontal coordinate system for that UGRC data in this video, but that's something that you should consider. And certainly if we look up at the horizontal coordinate system for the 30-meter World Geographic, that's not going to be compatible with the local Cartesian coordinate system of UTM Zone 12 North. So we'll need to convert that into that Cartesian coordinate system. And the vertical datums, some of them are different. So NAVD88, Geoid 12B for the LiDAR, both of them, that's great. We can go ahead and pretty much difference them right off without doing any real changes to them. These other ones, we can do the differencing, but we're going to get differences that are purely due to differences in vertical datums. So we have, in the case of the 2006 UGRC data, it's a geoid 03 model, so it's an older geoid. There could be some differences there of some centimeters or so. And then here it is a 1996 geoid. I believe I got the geoid model, not the ellipsoid one. So I should actually delete that. So yeah, so we have geoids in all cases, but different additions. Now, if you wanted to convert those geoids, it's tricky to do. I know that if you take geospatial field methods class in our GIS certificate program, you'll get good and practiced on this. There are resources for doing this. One is the online vertical datum transformation tool through NOAA. But it requires certain file extension types to be put in, such as an ASCII2 file format. And then ArcGIS Pro also has some tools that you can use, but it's not as kind of plug and play as you might like it to be. So keep that in mind. You might need to figure out what your metadata says, insert a file. It'll spit out a new file based on kind of a transformation of those heights above the correct geode model. Okay, so that is what we're dealing with in terms of metadata. And remember, the way to get at that metadata can be found in the case of Open Topography on the website through links, on here by downloading these reports. And go ahead and open them up. With UGRC, we see that they give things like these QA reports, which will tell you about root mean square, vertical and horizontal positions if we scroll down through. So that's great. And so all that metadata, you want it all. And so I've quoted some other things in here in the units and quoted accuracy. And so we can see that the LiDAR's quoted accuracy is in the order of tens of centimeters, whereas the regional scale DEM's vertical and horizontal accuracy is more like in the order of meters to 10 meters. And so some of the differences between these is going to be due to inaccuracies. Some of it's going to be due potentially to real things. And some of it's going to be due to the fact that some of these data are terrain models and others are surface models. And so we're going to go ahead and do this and compare them. In the next video, we need to kind of transform the coordinates and make sure that we've got things kind of over the same exact area to do the vertical differencing, because it is much easier to visualize if the data sets align with one another and don't have holes in them where you're differencing 2000 from no data, where we get big ranges in values. Because most of the changes in difference is going to be small, potentially, especially because we're just talking about a few years. And not much has happened. Geology is slow. Little erosion along a riverbank, something like that. A house was built, etc. Okay, so that's our introductory video. Next video, stay tuned.